Okay, so we should be live. Let me, where's the chat? There it is, okay. All right, so let's get going. Switch over to the Elgato and to MAT112. Okay, so last time, because of course it was Friday, last time we talked L'Hopital's rule. Also, those of you guys who are online, I was just mentioning to the everybody here in the room that if you haven't had a chance to do or work on task 2, which was to use Mathematica Online, or Wolfram Online, I guess they call it, please try and complete that by before class on Monday, because we're going to be using Mathematica in class on Monday. So that way you guys will be ready to go for that. So, all right, so last time we were we did L'Hopital's rule, okay, and one of the reasons that we needed to do L'Hopital's rule was to start talking about improper integrals. Okay, so what makes an integral improper? There's two different ways that it can be improper. Jack, what's one of them? Okay, so either okay, either A or B is infinite, possibly both. Okay, um, but um, okay, so that's one way that an integral can be improper. What's another way that one can be improper other than Jack? Jack's already got one good answer for us, so what's another one? All right, Jack, save the day. Yeah, so now as it turns out, continuity is not the end of the world to break, but if it's undefined, we definitely have a problem. Okay, so if F is undefined or perhaps discontinuous somewhere on the interval a to b. Okay, and that could be at one of the endpoints, or it could be at some point in the middle somewhere. Okay, and so discontinuity. Well, what makes a function continuous versus discontinuous, right? So, how did you define continuity in high school? Yes. Okay. Right. Those were the things that sort of looked like discontinuities. You had holes, jumps, asymptotes, those sorts of things. Okay. So if you didn't have one of those, then you'd be like, oh, well, it's continuous. Okay. Uh, so what's sort of the high school definition? How can you tell if a function is continuous? If you graph it and you don't have to pick up your pencil, right? That's the high school definition. What's the college definition of continuity? And all those three things are equal, right? So the college definition of continuity is that at the point, okay, so continuity is a property at a single point. And then if you say it's continuous at a bunch of points, you're saying it's continuous at each one individually, okay? So continuity would mean that one, you're defined at that point. You can't be continuous if the function is not even defined, okay? And two, the limit as x approaches that point exists. And 3, those two answers have to be the same, right? So if the limit is 5, but the function's value is 7, that means that there's a jump, okay? If the limit is 5, but the function's undefined, that probably means there's a hole, okay? And if everything goes haywire, then there's probably an asymptote, okay? So that's sort of the encoding of the high school definition, but in precise terms using limits. Okay, so continuity, as it turns out, what's really going to be the problem here is not so much discontinuity, but if there's actual undefinedness going on, okay? As we'll see in a moment. Okay, so if, for example, we have a situation like this, okay? Oh, and I should mention, by the way, that is it possible for an integral to be improper in both ways? Is it possible for it to have an infinite bound and also have a continuity problem? Totally, right? Now, you hope that that doesn't happen because that means you've got a lot of work to do, but it totally can happen that an integral can be super improper. Um, well, like say, for example, the integral from minus infinity to infinity of 1 over x. We've got infinite bounds, but 1 over x also fails to be defined at 0. Okay, so it meets both of these criteria of improperness. Okay, now what we do to deal with that is another matter, right, which we'll obviously get to. Okay, so let's just take sort of a couple different individual situations of improperness and see how we're going to deal with the problem. Okay, so first off, let's say that we have an infinite bound, and I've written here a to infinity, but this could just as easily be negative infinity to a or whatever, right? So how am I going to think of this problem? Okay, what's sort of the way out of the trap, pun intended? Yes, Mr. Trap. Yeah. Okay. Yeah, whatever. All right, so what we'll say is that the integral that we started with here, a to infinity, is improper because of the infinity. And so the solution is we'll think of improper integrals as really being limits of proper integrals. Okay? We know how to deal with proper integrals. We hopefully also know how to deal with limits. Okay? And there we go. Okay? Now, this limit the limit may or may not exist, right? Depends on the function, depends on the numbers, all of that jazz. Okay, so if the limit exists, then it means it's a number of some sort. Okay, okay, so if, suppose it exists, and it has the value L for limit, whatever. Okay, then we say that the original integral converges to L. F of x, yeah, sorry. Let me clean that up a bit. So we got 5 people online today. Let's see who we have. Mr. Hall, you hanging around from computer science? Farden, I see you here. And then we have the world's saddest kitty. I don't know who that is. Huh? I don't know. You never know with the internet, right? Okay, so that limit could exist or it doesn't. And if the limit doesn't exist, then we say that the original integral diverges, okay, or fails to converge. Okay. Okay, so that's sort of the terminology, right? These limits can either exist or not exist. If they exist as a number, then the integral will say converges to that number, and otherwise we'll say it diverges. Okay, good? Now, there is one minor problem. So, well, there's a lot of minor problems. Let's take, for example, this. Converge, what do you think it means? Just think of the word. Yeah, it approaches that value. Okay. Diverge means it doesn't approach any value. Okay. Good question. Okay, so that's a very good question, actually. Um, let me let me actually switch over to Mathematica and let's do a graphical example to illustrate this. Okay, so I'm going to switch the projector on one of them over to the computer. Okay, and then I'm going to switch the, let me get Mathematica open. And then I'm going to switch the stream over to the, the computer and hope that I didn't screw anything up. Okay, that's interesting. You see my login screen, not my desktop window. Okay, let me figure out why that's the problem. There we go. Okay. So on the stream, it was showing the login screen, not what you guys were seeing on the computer, and I'm just making sure that it's now it's not streaming at all from the screen. Okay, hold on. Okay, that works. So sorry for the technical problems, guys. We actually moved rooms a minute ago, I mean, from one room to the other. Okay, this is going to be annoying. All right, let me cut the stream guy. Oh, wait a minute. Why is that? Oh, I see what the problem is. Okay, transform, fit to screen, transform, stretch to screen. Okay, I think I can fix this. Why is this not loading? Okay. Okay, there, I think I've got it. Okay, Kapla, got it. All right, so let me blow this up a little bit. So let's take just an example function. And I'm just going to pick 1 over x, okay? And so if I plot that function from 1 to 10, right, we get our usual little hyperbola. And if I'm talking about the integral from 1 to infinity, then what I'm essentially asking is what's the area under this curve going all the way out to infinity. Okay, now let me actually add one other command in here. There, okay. So from x equals 1, which is here, the function is up there at 1, okay? And this thing keeps going off to infinity towards y equals 0 is an asymptote, yes? Okay, and the integral is asking what's the area under the curve, right? Yeah, the area between the x-axis and the thing, right? I'm sorry? Really? Well, yes, because coronavirus. Okay, we should talk later. Okay, yes, but what the integral represents is, well, did you guys do Riemann sums where you like drew little rectangles and you added up those areas? Okay, we'll talk later. Okay, just trust me that what the for now that the integral is asking is what's the area here, right? Okay, now that area you might say, well, it should be infinite because this curve goes off to infinity. It never crosses the x-axis, and therefore there's infinitely much area there. But that's not how math works, right? So what do I want to do with the integral? Let me actually define a new function, and let me call it g of t, and I'm going to do the integral of f of x from 1 to t. Or actually, I think it's integrate. Okay. And now, what is the definite integral of 1 over x? Or sorry, the indefinite integral. What's the antiderivative of 1 over x dx? Logarithm? Yeah, natural log. Okay. But in the computer here, Mathematica always writes natural log as just log, log, because what other kind of log do we use in? Yeah, exactly. 100% USDA certified natural logarithms. Yes. No preservatives or artificial sweeteners. Okay. All right. So, right. So I didn't really need to actually define this thing as a function because I know what it is. Okay. But if I plot that function from 1 to say 100, then what the y value of this function represents is the area that I've sort of accumulated up to a point. Okay, so you remember on the iPad I said I'm going to think of the integral from 1 to infinity or a to infinity as being the integral from a to t and then take the limit as t goes to infinity, right? So on this second graph, the one that's the graph of the logarithm curve, t is what's running along the bottom axis, and then the area is the number that's running along the vertical axis. Yeah, Cole. Right, exactly. Right. So I'm not talking about the area under this, but the y value of this curve tells me the area that I've accumulated under here. So like maybe 10 would be a better example because we've got 10 on that graph. If I go up here, I'm at like 2 point something, right, roughly. And then if I look on my graph here, from here over to 10, does it look like I roughly have 2 units of area? Yeah, close enough, right? So that's what the second graph means. Okay. And I could draw this on graph paper and like count it up and stuff, but yeah, close enough for government work, right? Okay, now the logarithm function, does this curve look like it's approaching any specific real number? It looks like it might be, but of course the graphs can be deceiving. Yeah. And so what we're essentially asking is, what is the limit as t goes to infinity of log t? Is that a specific number or not? Turns out it's not. Okay, so the logarithm function does grow infinitely. Okay, and I can prove why that's the case, right? There's no asymptote. Well, okay, sorry, no horizontal asymptote. There is a vertical one, right? Uh, over here at close to the origin. Well, it's increasing, but at a decreasing rate. Slow down and hit a, yeah. Okay, so this is why it's really important that you guys get plenty of sleep, because what we are dealing with, right, the mysteries of the infinite. I feel like you should be wearing robes and there should be like dark, candles all over the room and stuff. Yeah, there you go, like that, right? So I'm going to start my math cult here, um, and we're going to study the mysteries of the infinite, right? Um, it is worth pointing out, by the way, that there have been math cults throughout history. Pythagoras is the most famous example. He was that bunch that was totally a cult. Well, true, right? They didn't all like drink Kool-Aid when a comet came by or something. Oh yeah, in the 90s there was a comet, the Hale-Bopp comet. It was great because it was when it got really close to the sun, like you could look up at night and see it naked eye. It was beautiful, absolutely beautiful. But there was a cult in California, I think, of course, right? Uh, that thought that it was like a spaceship that was coming to take them to another dimension or something, and so they all drank like suicide punch. And yes, yeah, it was pretty crazy. Um, yeah, it was in the like 96, 97, somewhere in there. Huh? Well, I think it was California specifically, but yeah. Um, okay, so no, the Pythagoreans were a cult, and one of their more hilarious tenets was they were vegetarians. Okay, whatever, but they didn't eat beans. Now, if you're a vegetarian, especially in the ancient world, it's not as if you have tofu veggie patties, right? Those hadn't been invented yet. You need stuff, but beans. So now here's what's hilarious though. Why did they not eat beans? Well, what? Okay, we're at a men's college. We were all 12 once. Why don't eat beans? Yes, exactly. And iamblichus, so Mr. Trapp said because so they wouldn't fart. Yes, Iamblichus's Life of Pythagoras. Okay, so this is an ancient biography of Pythagoras. Says that, quote, one of their tenets was to not eat beans, for they are flatulent. Yes, they produce gas. So yes, that was 100% a thing for the Pythagoreans, which I think is hilarious. So anyway, um, okay. So anyway, so let me go back to the iPad for a moment, and let's just show why it is that what we've observed graphically here is in fact true. Okay, so that you guys can all see the right-hand screen. Okay, okay, great. And I've switched the input on the stream so that they can see the iPad. Man, this is so much better than the other room. Okay, so let me actually just, we'll come back to that double infinity example. We're looking at this, right? And we said that this will interpret as the limit as t goes to infinity of 1 over x dx from 1 to t, right? So the an improper integral we'll think of as the limit of a proper integral. We know how to deal with proper integrals. We hopefully also know how to deal with limits. Having L'Hopital's rule in our toolbox will help. That's why we did that first. Um, okay, and so let's deal with the problem. So we've got this limit. We'll blow off that part for now and think, all right, what about the integral? Well, what's the antiderivative of 1 over x? Right, we said it was natural log. Okay, so the antiderivative is natural log. Fundamental theorem says plug in the t, plug in the 1, and subtract. Okay, what's the natural log of 1? Yeah. Okay, the natural log of 1 is natural log of 1 is 0, so we can just dispense with that thing. But even if it wasn't, it's just a number, so yeah. Okay, so what we're left with is we've turned the question about this integral into a question about this limit. Okay, and I claim that this limit doesn't exist. Yes. Proper, yes. So this integral, let me highlight it. This integral is proper because is there any place where 1 over x is undefined from 1 to t? The assumption, of course, is that t is bigger than 1, right? There's no infinity and there's no undefinedness, so it's proper. Now, yes, there's a limit out front of it, but it's the integral itself, the one that I've boxed in red there, is proper, right? So again, improper integrals, express them as a limit of a proper integral, deal with the proper integral, then take the limit. Okay, Gucci? Gucci. Okay, so what is the limit as t goes to infinity of log t? Well, it's a good question, right? It happens to be, oops, infinite. Okay, aka um, accept it, know it. I could prove why that's the case. Okay. Um, Actually, to prove it's not that difficult. Okay. So let me just prove that limit while we're at it, why it is in fact infinite. Okay. So suppose it's not infinite. Okay. Suppose the limit as t goes to infinity of natural log of t equals L. Okay. Let me say it this way. What I'm going to do is I'm going to show you pick a value, Cole, as big as you want. Well, you were just in computer science class where we were just
6.02 times 10 to the 23rd.
exactly. We were talking about really big numbers. So if you pick 6 times 10 to the 23rd, I claim that I can find a value of t so that if we're further to the right than that point, then the function log t is bigger than your value, right? Well, we know it's increasing, but what I'm claiming is that it's increasing and there's no horizontal asymptote. Okay. Um, and so this is basically saying, suppose there's an asymptote, or maybe think of this as like, did you guys play limbo when you were kids? Right, the stick, and you have to like get under the stick. Yeah. Okay. So this is sort of the like pole vaulters version of this. No, if you tell me that no matter how high I set the bar, you can jump over it, then what have you just told me? You can jump infinitely high, right? And that's essentially what I want to do for the logarithm function is prove that it can jump over any bar. Okay. And so the way I'm going to do that is you pick a number capital T. Okay. If, for example, 6.022 times 10 to the 23rd, I'm going to prove that the logarithm function eventually gets bigger than that and stays bigger than that. Okay. Is that all right? All right. So um, I claim that the natural log of t um, eventually exceeds this limit. Okay. And or your supposed limit. Okay. So how could I find the t that makes that happen? Well, I could just exponentiate both sides, right? Okay. So if so, example, Cole picked 6.022 times 10 to the 23rd. It's a big number. Okay. If t is bigger than e to the 6.022 times 10 to the 23rd, then log t is greater than 6.022 times 10 to the 23rd. And therefore, 6.022 times 10 to the 23rd cannot be the limit. But you picked that 6.022 out of thin air, right? It didn't matter about that number. I figured out a way to do this no matter what big number you gave me, right? And so what that means is that there can be no limit. Uh, yeah. Okay. So now, just for sake of clarity, what is e to the 6.022 times 10 to the 23rd? Oh, it's going to be a gigantic number. All right, let's see. Oh no. Oh no 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 no. Yeah yeah yeah. Okay. Why? I need to switch back over to Mathematica, and of course I have not made a preview thing for that. Okay. So I've got Mathematica on here. Overflow, right? Well, yeah, but see, it's even worse than that because Mathematica can do arbitrary precision computation. Um, so, well, all right. So let's just say, well, okay, that's e to the thousand. Okay, 2.7 something, 2.71. Well, here I'll just show you. Um, because Mathematica is amazing. No, this I'm running it natively. Yeah. Okay. Um, so, all right, E is like 2.718, blah, 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 blah. It's a number like pi that the decimals keep going forever. It's irrational. It's also what we call transcendental. Pi and E are the only two transcendental numbers you guys know examples of. Um, huh? Get out. Yeah. Okay. So Mr. Trapp said tau. So some people, instead of talking about the number pi, okay, so what is the number pi? It's the ratio of the circumference to the diameter of a circle, right? Some people instead say, well, why don't we talk about the ratio of the circumference to the radius, which is double pi, right? So 2 pi is a constant that some people call tau, and they base everything around tau instead of around pi. Not infinite, it's just that you can't express that ratio as a ratio of whole numbers. Okay, so that's what it means to be irrational. The transcendental thing is a lot more complicated, and we can talk about that privately. Okay, but my point here is that e to the 1,000 is absolutely gargantuan, right? So e to the 10 to the 23rd, like we're talking a number that's so large, it's vastly more than the number of subatomic particles in the observable universe. It's so big that, I mean, but it exists, right, as a number. It's just so big that we can't even wrap our minds around how big it is. Okay, so all that to say is that the logarithm doesn't converge to any specific number. And so what that means is that our, let me go back to the iPad. This, what we basically just proved was that idea, okay, that the limit doesn't exist, and therefore the integral in this case diverges. Okay, is that all right? But it all came down to the limit. Now you might say, wait a minute, Dr. C, aren't these all going to diverge? Well, could I come up with another example where it does work? Of course, right? Because I wouldn't have asked the question otherwise. Okay, so let me come over here and let me pick a different problem. Similar, very similar to the one I had a minute ago. Sorry. And instead of 1 over x, I'm going to do 1 over x squared. Looks similar. Okay, but something magic's going to happen. Well, maybe not magic. So first off, how do I think of an an improper integral? I need to think of it as the limit of a, okay, limit as t goes to what? In this case, infinity, of a proper integral from 1 to t in this case, of 1 over x squared dx. Okay, so again, improper integral is a limit of a proper integral. Now we need to do the proper integral, and then we'll take the limit. We'll see what we get. Okay, does that make sense? Okay, so how do I do this integral? What's the antiderivative? What do you mean identity? Yeah, so what's the antiderivative of 1 over x squared? How do you write 1 over x squared? Huh? Right? Okay, so what's the antiderivative of that? 1 divided by negative 1, right? Which is what I just wrote there. Okay? Good? Gucci? All right. So if I do the fundamental theorem, I have to plug in a t and subtract what I get when I plug in the 1. Right? So that gives me negative 1 over t plus, because I've got a double negative, 1 over 1. Okay, good. We Where? No. They are supposed to be t's because I plugged t in for x, right? So x I'm thinking of a variable, t I'm thinking of as a number that is I'm sending off to infinity. Yeah, so it is written correctly. I mean, you could whine and complain about my handwriting, but it is written correctly. Okay. Trust me, I'm a doctor. Okay. All right. Now, what's that limit? Well, what's the one part? 1 over 1. Okay, yeah, the limit of 1 is 1. It's a constant. But what about as t goes to infinity, what does negative 1 over t do? It goes to 0. Okay, why? If I'm dividing by gargantuan quantities, what's 1 divided by a gargantuan number? 1 over it. It'd be really tiny, right? So as x goes to infinity, or t goes to infinity, what's 1 over t do? It goes to 0, right? And so this limit approaches 1. Oh, hello, Ben. I'm glad you could make it to class this week. No, Ben from the high school. So the high school is doing this crazy, like, they go to school like in person on Monday, Wednesday, Friday, and do it online Tuesday, Thursday, and then the next week they do it the other way. So like every other week he can't come to class. Yeah. So anyway, and Ben, please check your email because I wanted to talk with you over Zoom at some point. Okay, so we got 1. Now let's go back over to Mathematica and oops. Let's go back over to Mathematica because what I want to do is let's graphically analyze exactly what we had. Okay, so what I'm going to do is I'm going to change the x to x squared and redo the exact computation. Okay, and what does, so the top graph is 1 over x squared. Okay, and I'm asking what's the area between it and the x-axis as I go off to infinity. Okay, it looks visually like the last one, right? You might say, well, Dr. C, there's a horizontal asymptote there. It's not going to get there. There's an infinite amount of area. But in a sense, what's happening is that this 1 over x squared function is decreasing fast enough, and I'm going to put that in giant air quotes, that the area here gets squeezed in and converges actually to a number. Okay, and we can see exactly what that number is because what's the second graph? That's my area up to a point, right? So if I look at, say, the 100 on the horizontal axis there, if I go from 1 to 100, what's the total area enclosed under the top graph? Well, it's 0.98 something, right? Okay, so whatever the y value is at that point. So 0.98, whatever. Does this second graph look like it is approaching horizontal asymptote? It is. Okay. It looks the same. Well, and this is why we don't just use graphs to answer these questions, right? This is why we have the symbolic stuff with limits and antiderivatives and whatnot, because the graphs are misleading, right? But the limits are not misleading, or at least they better not be. Okay, does that kind of make sense? Okay, so no, so the question was, what's the characteristic of a graph that either does or does not approach something? That's an impossible question to answer graphically. Well, okay, the function would be converging to something or not. Yes, the limit of this function as t goes to infinity is 1. Okay, so the value converges to 1. The value of the previous problem that we did not converge to anything specific. Okay. Now, graphically, how do I know that? I don't. So how do I know this really? Because of all the limit stuff we did on paper, right? So the graphs can be, useful to sort of build an intuition. Okay, but here's sort of the big thing. We're dealing with the concept of the infinite. And if there's any one thing that I've learned in all of my life being a disciple of mathematics, is that your intuition and the infinite cannot go together. Okay, you have to throw out your intuition and you have to work systematically and deductively using definitions and logic and reasoning. You cannot trust your gut when it comes to the infinite, because if you do, you will go insane. You might argue that we already have gone insane because we're even having the conversation in the first place, but that's another matter. Okay, so do not use your instincts when it comes to the infinite. You will burn yourself. Okay. Um, okay. So just to sort of recap, what did we talk about today? The fundamental, well, two fundamental things. One, how can an integral be improper? It can be improper because there's an infinity at one end or the other, possibly both. Or it could be improper because the function you're integrating isn't defined somewhere along the region of integration. Integrals can be improper for both reasons, and those are a nightmare and I'll work one of those examples first thing next time. Okay, because something really subtle comes up when you have that. Okay, so there's that. And then also, what does it mean how do we deal with an improper integral? We think of it as the limit of a proper integral. If that limit exists, comes out to be a number, great. The integral converges to that number. If it doesn't converge as a limit, then the integral, we say, doesn't converge. So we've turned the problem from one into something else. Okay, now, because we're dealing with limits, I mean, the two examples that I worked here were relatively straightforward from the computational aspect. But limits, right, need work to figure them out. And sometimes they need a lot of work, right? Because what are the techniques of limit finding that we have? Well, you got the stuff that you guys learned in Calc 1. And then now we also have L'Hopital's rule in our toolbox. Okay? All right. So we'll quit the stream here. And again, just a reminder, if you have not already looked at task 2, which is the Mathematica Wolfram Online thing, please try and get that finished by Sunday night so that you're ready for the Mathematica that we're going to be using in class on Monday. All right, I'll cut the stream, and I'll see you guys on Friday.